At the turn of the 20th century, scientists began to picture the atom as a nucleus of positively charged particles, surrounded by an equal number of negatively charged electrons. The American chemist Gilbert Lewis believed the electrons in the outer shell of an atom are the key to chemical bonding. Lewis's octet rule, first published in 1916, proposed that the atoms of all elements have between 1 and 8 electrons in their outermost or valence shell.
The periodic table lists all the substances in the universe that have only one type of atom in their makeup. Countless millions of other substances are made from combinations of these atoms. When atoms come together, they form bonds, and the resulting molecule or compound has a whole new set of chemical and physical properties. So let's look at chemical bonding and start with the most abundant atom in the universe, hydrogen. The element hydrogen has one proton and one electron, making it quite simple. The proton is positively charged in the center of the atom, and the electron is negatively charged and occupies a larger space outside the nucleus in the form of an electron cloud. This electron cloud surrounding hydrogen is often called an orbital. It is basically all the places where an electron has a chance to be found. Now let's bring another hydrogen atom into the picture. As we slowly start moving them closer to one another, we will show their combined energy on this graph. For a while, nothing changes. And then as they get close enough together, their energy starts to drop and eventually hits a minimum. And this makes the combination stable. This minimum energy distance between them is called a bond distance. And they are now sharing electrons. This is called a covalent bond. And instead of having two individual hydrogen atoms, we now have an H2 molecule. Moving the atoms any closer increases the energy greatly, since the positive protons in each of the atoms are repelling one another strongly. Covalent bonds come in different lengths and strengths depending on the atoms involved. These bonds are often shown as posts, lines, or dots between atoms. But of course, these are simply representations of places where electrons spend their time between atoms. In a covalent bond, electrons are shared, but they aren't necessarily shared equally. Let's take one of the hydrogen atoms and replace it with a fluorine atom. Watch what happens to the electrons throughout the atom. Fluorine, by its very nature, has a stronger pull on electrons in this molecule than does hydrogen. Fluorine shares electrons, but not equally. Instead, it pulls electrons closer to itself than to hydrogen. This is called a polar covalent bond. Each element in the periodic table has a tendency to pull electrons towards itself in a bond. This property is called electronegativity. When you alter the periodic table to show electronegativity, it looks a little different. Notice that elements on the left-hand side of the table, metals, have very low electronegativity values. They don't pull electrons towards themselves at all. As a matter of fact, they willingly give them up entirely. Table salt, as we know, is made up of sodium and chlorine, and so it is called sodium chloride. In forming table salt, the sodium atom gives up an electron and becomes positively charged. The chlorine atom picks up the electron since it is more electronegative and becomes more negatively charged. Now a very old saying takes over. Opposites attract. So here, the atoms are drawn towards one another by their positive and negative charges. If there are enough atoms, we can eventually wind up with something as big as a single salt grain. This kind of bond is called an ionic bond. It is a very strong attraction between positive and negative ions. Most people differentiate this from a covalent bond by saying that in ionic bonds, electrons are exchanged instead of shared. Ionic bonds are very strong, stronger than covalent bonds. And you can easily see this difference. Melting sugar, which is breaking a covalent bond, is simple and makes caramel. Melting table salt is very different and requires temperatures higher than 1400 degrees Fahrenheit. Ionic bonds are very stable bonds. Very important, and much weaker than ionic or covalent, is a hydrogen bond. When hydrogen atoms connect to a small, strongly electronegative atom like fluorine, oxygen, or nitrogen, the resulting molecule pulls the electrons so strongly to the larger atom that the hydrogen nucleus, its one proton, is essentially exposed on one side. So it will bond to the negative side of any similar polar molecules. This bond is called hydrogen bond. The difference in strength of the different types of bonds is fundamental to allowing the DNA molecule to replicate itself. The bonds that hold the opposite sides of the double helix together, the A's and the C's and the G's and the T's, are hydrogen bonds and are very weak compared to the bonds that hold each letter to the backbone and the bonds that hold the backbone together. This allows the molecule to unzip easily, to expose one side as a template for replication. Life is all about bonds. Bonds, chemical bonds. Who knew?
Chemical changes had me a blast.
Chemical changes happen so fast.
I made a chlorine, crazy for me.
I made a sodium, cute as can be.
Chemical changes taking place to a new substance is formed. How did it happen?
Tell me more, tell me more. What fun did it form? We're on opposite sides of the table.
I'm on the left, so I am the middle.
Things got heated and it got hot.
We then formed an ionic bond.
Chemical changes, something you form, but of those chemical reactions. Tell me more, tell me more. Was it love at first sight?
Tell me more, tell me more. How did you bond? We went bonding in the lab.
We then found the perfect match.
I have a charge of -1.
I have a charge of +1.
Chemical changes, ionic bonds will always form ions.
Tell me more, tell me more.
What new substance formed?
Tell me more, tell me more. Because the third substance was made. We then bonded from sodium chloride.
In this reactant, reactants on the left-hand side.
All the products are on the right.
Valence formula shows what it's like.
Sodium chloride may taste salt, so it's a synthesis reaction. Tell me more, tell me more. What's the decomposition?
Tell me more, tell me more. Did you break up?
It turned color, endothermic reaction.
We then broke up, lost the attraction.
We went back to the way we once were.
What I'd give to be back with her. Substances broken down. So it's a decomposition reaction.
Ooh yeah, ionic bonds, covalent bonds, both of them chemical bonds. How are they made? What's the difference? Watch, you'll see. First we'll start with ionic bonds. A metal and non-metal are involved. The metal gives over electrons, the non-metal it receives. The atoms become ions. The metal might have 1, 2, or 3 electrons for the non-metal to receive. It all depends on what's needed to make the number 8 for the non-metals our shell. And if it happens for them, they both become ions. Charged atoms, they become ions. The metal's positive, the non-metal's negative. They become ions. Oh yeah, the metals plus, the non-metals minus, and opposites they do attract. So what you get when they come together is an ionic bond. Sodium chloride. So what about those covalent bonds? It's not about loss or gain of electrons. Valence electrons, they are shared to complete the outer shells of the non-metal central bond. It's when non-metals join to make covalent bonds with shared electrons. They're covalent bonds, not a transfer. Instead, they share valence electrons. Oh yeah, ionic bonds, covalent bonds, both of them chemical bonds. How are they made? What's the difference? Play the song again.